Today, we're really digging into one of the absolute biggest puzzles in modern physics. It's this challenge of unifying the universe's fundamental laws.
Yay. It's a huge undertaking.
Because you have these two incredibly successful theories, right?
Yeah.
General relativity that gives us gravity, the cosmos, black holes, all that large-scale stuff.
Masterfully describes it.
And then you have quantum mechanics, rules the subatomic world, particles, forces, everything tiny.
Incredibly precise there.
But here's the rub, and it's a big one.
Yeah.
They're fundamentally incompatible. You try and
What?
put them together mathematically.
It falls apart. The equations give you nonsense, basically. Infinities pop up everywhere.
Which tells us pretty clearly our picture is incomplete. Something's missing.
Exactly. And that's where string theory enters the picture. It's probably the leading candidate right now in this huge quest for a theory of everything. A single framework, to bring all the forces and all matter together.
So our mission today is to unpack what string theory is actually proposing. It's pretty radical stuff, right?
Oh, absolutely. We want to understand why it's considered such a powerful idea, such a potential solution to that deep incompatibility we just mentioned.
Okay, so let's get into that radical idea. String theory says, forget point particles.
That's the core shift. Instead of zero-dimensional points, like tiny dots, the fundamental constituents are, well, one-dimensional strings.
And these are small, right? Like unbelievably small.
Unimaginably small. We're talking around the Planck length. That's 10 to the minus 33 centimeters. Way, way smaller than anything we could ever hope to see directly. Which, is why they look like points to us in our experiments.
Okay, but why does that length, that one-dimensionality, actually help with the physics?
Ah, that's the crucial insight. Because they have this tiny, finite length, strings aren't points. So when they interact, the interaction isn't happening at a single, infinitely small point. It's sort of smeared out over the length of the string.
Smeared out.
Yeah.
Okay.
And that smearing, that tiny bit of fuzziness, is mathematically exactly what you need to eliminate those problematic infinities that plague other attempts to combine quantum mechanics and gravity. It's not just patched in, it emerges from the idea of strings themselves. And these strings, by the way, can be open with ends or closed loops.
Right, okay. And then there's this idea about vibrations. That sounds fascinating. How does that explain all the different particles we see?
Yeah, this is where it gets really elegant. Think of a violin string. Pluck it one way, you get one note. Pluck it differently, you get another note, right?
Yeah, different frequencies.
Exactly. String theory says all the different fundamental particles, electrons, photons, quarks, everything, they're just different ways a string can vibrate. Different resonant patterns.
So it's not different types of strings for different particles.
No, that's the beauty of it. It's one single fundamental type of string. Its vibrational mode determines everything about the particle. It appears as its mass, its charge, its spin. It's like the universe is playing music on these tiny strings. And here's a really compelling part. One of the natural vibrational modes that just falls out of the mathematics of string theory corresponds precisely to the properties predicted for the graviton.
The particle that carries gravity.
The very same. So gravity isn't something you have to force into the theory. It's just there. It emerges naturally as one of the string's possible vibrations. That's a huge point in its favor for a quantum theory of gravity.
Okay, now for the part that really stretches the imagination. Extra dimensions.
Yeah.
More than the 3 space and 1 time we know.
Haha, yes. This is definitely mind-bending. The maths of superstring theory, the most developed versions, don't work in just 4 dimensions. They consistently require 10.
10 dimensions. Where are the other 6?
Brother, and its big brother, M theory, needs 11. So yeah, where are they? The idea is compactification.
Compactification.
Meaning these extra dimensions are curled up, really, really tightly curled up. On scales even smaller than the strings themselves, probably near the Planck length again.
Like the garden hose analogy. From far away, it looks like a line.
Exactly. Looks one-dimensional. But get close, like an ant walking on it, and you see it has a circular dimension, its circumference. These extra dimensions are supposedly curled up like that, just incredibly small, so we don't perceive them in our everyday lives.
But do they do anything if they're hidden away?
Oh, absolutely they do. According to the theory, the precise way they are curled up, their specific shape, their geometry, directly influences the types of string vibrations that are possible, and therefore it dictates the kinds of particles and forces we see in our familiar 4 dimensions. The geometry of the hidden dimensions literally shapes the physics of our universe.
That's quite a concept.
Sure.
So it sounds incredibly elegant, mathematically powerful. But what are the roadblocks, the big challenges?
There are definitely significant challenges. The biggest one is direct experimental proof.
Right. The energy needed to see Planck scale stuff is astronomical.
Precisely. Way beyond anything we can currently build. Now, related to this, many string theories rely on an idea called supersymmetry.
Supersymmetry. Can you quickly unpack that?
Sure, supersymmetry, or CSY, it basically proposes a symmetry between the two fundamental types of particles we know. Fermions, which make up matter like electrons and quarks, and bosons, which carry forces like photons. It predicts that every known particle should have a heavier superpartner particle with different spin properties. So an electron would have a selectron, a photon, a photino, and so on.
Okay. So experiments like the LHC look for these.
They do. Finding superpartners would be huge news, and it would certainly provide circumstantial support for string theory, as CSY fits very naturally within its framework. But so far, we haven't found any evidence for these superpartners at the energies the LHC can reach. That's a bit of a worry.
And finding them wouldn't prove string theory anyway, right? Other theories use CSY too.
Exactly right. It would be consistent, but not definitive proof. And then there's another major theoretical hurdle, the string theory landscape.
The landscape. Sounds vast.
It is. Remember those extra dimensions and how their shape matters. Well, it turns out there seems to be an enormous number of ways to curl them up consistently within the theory. Maybe 10 to the power of 500 possible geometries.
Wow, 10 with 500 zeros.
Something like that. And each different way could lead to a universe with slightly different physical laws, different particles, different forces.
So how do we find our universe in that haystack?
That's the problem. With so many possibilities, it becomes incredibly difficult for the theory to make unique, testable predictions about why our universe has the specific laws it does. It leads to debates about whether string theory is even falsifiable in the traditional scientific sense. If it can describe almost any universe, how do you prove it wrong?
Right, that's a serious philosophical challenge too. So wrapping this up, where does this leave us? What should you, listening, take away from this? String theory, it's clearly still one of the most ambitious games in town, a potential path to that unified theory, offering deep ideas about black holes, maybe even the multiverse.
Absolutely. The quest for direct evidence is tough, no doubt. But the theoretical progress continues, and its mathematical consistency and sheer explanatory potential are why so many physicists remain deeply invested in exploring it. We're trying to figure out the fundamental rules of reality.
So here's a final thought to ponder as you go about your day. What if everything you see, everything you are, all the particles, all the forces, what if it's all just the intricate music played by unimaginably tiny vibrating strings, echoing through hidden dimensions we can't perceive? A pretty profound idea, one that, if true, would utterly transform our understanding of existence itself.